All right, so a base is a number 2 or greater, and the number of symbols is the number of the base. So base 2 has 2 symbols, 0 and 1. Pretty simple. It is the most simple base. So to count, binary and decimal, you go 0, 1, run out of symbols, you roll back over to the lowest value, 0, and then add 1 to the next column, the next digit. So that is 0, 1, 2, add 1 for 3, add 1, rolls over, carries a 1 over. 1 and 1 is 2, but 2 is 1, 0, so 1, 0, 0 is 4. And 1, 0, 1, 1, 1, 0, 1, 1, 1 are 5, 6, and 7 respectively. Okay? Fairly simple. You just have to adjust your thinking to roll over to 0 after 1. Roll over to 0, carry the 1 into the next column. The digit's position is equivalent in decimal to 2 to the 0th power, 2 to the 1st power, 2 to the 2nd, 2 to the 3rd, etc. So this would be the 1's position, the 2's position, the 4's position, and the 8's position. So to get in the example here, 1, 1, 1, you have 1, 4, 1, 2, and 1, 1. So it's 4 plus 2 plus 1 equals 7. Simple way of doing math and expressing lots of digits, expressing numbers with lots of digits. So if you have 3 digits, you can only binary digits. You can only express 0 through 7, or 8 digits. So, or 8 values. So you take the number of, to get the number of values you can have, you take, say you have 4 digits. You take 2 to the 4th minus 1, and that's your max value. And 2 to the 4th is number of values. So 4 digits, 4 binary digits is 2 to the 4th is 16 minus 1 is 15. So the maximum value you can express with 4 digits is 15 value. The maximum value is 15. The number of values is 16 because it's 0 through 15. Just a little bit of terminology. Binary oh, whoops. Nope, no. Binary digit is shortened to be a bit. That's where the word comes from. Binary digit. Computer scientists are often lazy, and rather than writing out binary digit, shorten it to bit. 8 bits is a byte. A long bit. Long I, long sequence of bits makes a byte. And for old graphics cards, like the original CGA graphics card back in the 80s, the memory was organized by groups of 4 bits. Computer scientists also happen to have a sense of humor. So what is between a bit and a byte but a nibble? A nibble is 4 bits. You don't see that very often anymore in memory organization. Memory is typically organized in bytes or words. 2 or more bytes is a word. So, and just for the sake of completeness, what would be between a bit and a nibble? 2 bits. Any ideas? Don't think computers. What would be a bit between a nibble and a bit? It is a crumb, yeah. 2 bits is a crumb. So, little terminology for you there. Yeah. The decimal? Or you mean this one? Okay, I put the plus signs there. Might be confusing there. There's 1, 4, so it's 4. There's 1, 2, so it's 2. 1, 1, so it's 1. Like, are you getting those numbers from the binary? Yeah, that's the binary. I was using the example of the 7. The 7 in binary is 1, 1, 1. And that's how you calculate the value from binary to decimal. You take the value of the binary digit, value of the bit, times the value of the position it's in, and then you add those all together. Okay. So we'll go with another example. Let's say 1, 0, 1, 1. What would that be in decimal? Plus, yes. So 8 plus 2 plus 1 is 11, which you'll pick up little things like this along the way. It happens to be the last 2 digits of the number there. On that, in this particular case, it's 11. Likewise, 1, 0, 1, 0 is 10. So it's easy to remember that particular combination. But yeah, converting from decimal to binary. No, that's use negative numbers. We'll get to that in just a minute. Decimal to binary. Say you want to convert 43 base 10 to binary. Okay, what's the highest power of 2 that will go into 43? What's the value of that? 32, yes. So 32, subtract that, and that's 11, right? You put 1 in the 32's position, and you have the 16s, 8s, 4s, 2s, and 1s. So you put a 1 in the 32's position, you subtract 32 from your original 43, and you get 11. What's the highest power of 2? 8. So no 16s. Put an 8, 1 in the 8 spot. Gives you 3. And keep doing this over and over. Subtracting powers of 2 without going negative. So there's no 4s in 3, but there is a 2 and a 1. So this is the right answer. But now 2's complement, which somebody brought up just a few moments ago, is how you represent negative numbers. Now, typically, you would have a certain number of bits that you're going to represent in this, and it's usually multiples of 8. So an 8-bit 2's complement is going to have 8 bits. So you're going to have say you want to make a number negative. Let's use the example of that 43. That was 132, no 16s, an 8, no 4s, a 2, and a 1. You want it to be 8-bit, so we only have 6 here. This is 32, and we want negative 32. So you convert it to binary, and you add leading zeros to fill out the 8 bits.
Thank you.
Bless you.
Thank you.
Bless you. Then you do the manipulation. You flip the bits and add 1. So flip the bits, then you add 1 to it. And that is negative 32. Okay? Now, you might have guessed that it doesn't matter how many bits you have. If you have, say, 12 bits, it'll just lead to more leading 1s. I say it would be actually 16, but I was running out of room, so that's why I only did 12. And then so you can use these numbers and add them to a positive number or another negative number and perform subtraction, because that's all a computer can do really is addition, and they have special circuitry for multiplication, but pretty much it's just addition. Computers can only do addition. Subtraction is adding a negative number. Multiplication is multiple addition, and division is multiple subtraction. So all a computer does is addition. Okay, and when we get into adders and stuff like that later in the course, you'll see how easy that is. Yeah. This? Oh, this is 32 as a positive number. To make it a negative number, you flip all the bits. 1s become 0s, 0s become 1s, and then you take that number and then add 1 to it. So this is separate. It's not 1 plus 0 plus 1.
You only add 1 to that.
Yeah, to the second number here. Oh, 40. Oh, I'm sorry. Yeah, the example was 43. You're right. Thank you for that. Yeah, 43, and then negative 43 as a, in this case, 12-bit 2's complement negative number. Okay? Got your heads wrapped around that one? Pretty much? Okay? We're going to go on and at least get started on hexadecimal. Hexadecimal is base 16. As you might have guessed, base 16 has 16 symbols. Rather than coming up with new symbols for new numbers, we use letters. So you run out of the normal 10 digits, 10 decimal digits, you switch to letters. So base 16 has 16 symbols. I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. And that corresponds to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Now the fun part about hexadecimal is it converts to binary super easy, because 0 is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. 1, 0, 0, 0. You know how I mentioned earlier that 4 bits, you could represent 15 values, or up to 15 with 16 values? There they all are. They match up perfectly with the hexadecimal digits. So, if you are going to convert from hexadecimal to decimal, or to binary, you don't have to go through decimal and convert to decimal and then convert to binary. You can just, like, say you have the number 4C8. 4 is 0, 1, 0, 0. C is 1, 1, 0, 0. And 8 is 1, 0, 0, 0. So it converts really easy, back and forth. You have a 12 a you have a 12 bit number converted to hexadecimal. This is here. That's A. 1001 is 9, and 0101 is 5. Easy peasy. As a matter of fact, I would recommend any quiz or test that you have, quickly jot this down, this conversion here, down, so you can do number conversions easily and accurately. Eventually, you might get this chart memorized, but and 2's complement works the same way with hexadecimal as well. Like let's go back to that 43 example. That 43 example was, let's see here, minus 43 was 1, 0, 1, 0, 1, 1 with 2 leading zeros, right? That was the 43 in binary? Yeah. Okay, flip the bits. Add 1. And then convert it to hexadecimal. So 1101 is D, and 0101 is 5. D5 is minus 43 in hexadecimal. As you can imagine, using hexadecimal uses fewer digits. An 8-bit number is reflected as a 2 hexadecimal digit number. So large numbers are often expressed in hexadecimal, so they use fewer digits. Memory locations can be quite large. You know, when you get into the gigabits, gigabit and or gigabyte and terabyte range. 1 gigabyte is, what is that? How many bits is a? How many bits is a 10? 3, 6. No, 10, 20, 30. 30 bits is for 1 gigabyte address, whereas you can express that as with, rather than 30 digits, 30 binary digits, you can express it with 8 hexadecimal digits. So it's a lot more space efficient to write. Often I find that if you're converting from decimal to hexadecimal, converting from because converting from binary to hexadecimal is easy. I find it easier to convert a decimal number to binary first, and then just do the simple substitution in to make it hexadecimal. And that's essential when you're dealing with negative numbers. You have to go to the binary, give it a 2's complement value, and then convert using the substitution to hexadecimal. Is there anything else about hexadecimal that you might need to know? Or, have I missed anything? Have I gone too fast? I'm used to a class that I have to squeeze in a year's worth of material in one semester, so I'm used to going really quickly, and that's not the case with this class. So I'm trying to learn to slow things down. Well, but When you're dealing with code, this is something that you have to make sure you make a note of. When you're dealing with, on the whiteboard or in your quizzes and tests and that sort of thing, you use subscripts to indicate what base you're using. You can't do that when you're writing a program. So, depending on the language you're using, some of these are acceptable and some are not. 0H, 0X are hex, 0B is binary. You put that as a prefix to the number to indicate the base of the number to the computer so it can tell the difference. For example, 140. Okay, it's obviously not binary, but is that decimal or is it hexadecimal? It could be either one. The symbols, it could go either way. So to indicate that it's hexadecimal, you would put 0x in front of it. Or 0H, depending on the system that you're using. Likewise, 1011. That could be binary, it could be hexadecimal, it could be decimal. You have to let the computer know with the prefix what it is. No prefix means it's decimal. It's just 1011. Put a 0B in front of it, it becomes 11. So when you're programming, keep that in mind. This will come up in computer organization and design. You'll learn assembly programming, which uses pointers that use hexadecimal and bit fields to control various peripherals on the processor. And you'll use those will use binary. So be mindful of this. You can, on the tests or whatever, if you want to express your answers using these prefixes, that's fine too. Either that or the subscript after the, 1011 base 2. That either one is acceptable. I can figure out what you mean. But if it's left with nothing, I'm assuming it's decimal. So, I think that will be about it for the day. I'm, like I said, moving a little bit fast because that's the pace that I'm used to from other classes. Monday is kind of a free day for asking questions. If you want to do examples on the board, that sort of thing, we'll take care of that on Monday. Wednesday, there will be a quiz on number systems. So be ready for that. Have a wonderful day.